Hi everyone, and welcome to this first video in a series about number theory. As mentioned in the previous video, which is mostly about giving motivation, an overview of some of the topics we might cover, we're going to do absolute values and what it means to have an absolute value on a field, what sort of results can come from that, and looking at the classification of absolute values on the rationals, which is going to be our big goal for this video. I initially intended to do discrete valuations as well, and DVRs, but since that's such a big topic, I think I might postpone that to a second video, which goes hand in hand with the first. So let's get started with absolute values and see what we can get from that. We define an absolute value on a field K as a map which goes from K to the non-negative real numbers, such that for any pair of elements in the field, the following three properties will hold. The first is definiteness, in that the absolute value of an element is equal to 0 if and only if we're taking the absolute value of the 0 element itself. Otherwise, the absolute value of any non-zero field element is going to be strictly positive. The second is homogeneity, or this multiplicative property. The absolute value of a product is equal to the product of the absolute values. And the third one is this familiar inequality, which is the absolute value of x plus y is less than or equal to the sum of the absolute values individually. So up till now, the usual absolute value on the real numbers, let's say, or anything that it descends to, so it descends to the rationals, for example, even the integers and so on, or taking the norm on the complex field, it does satisfy these three properties, and we can effectively reason with Archimedean absolute values, as we'll look at in a second, by thinking of those on the reals. But these three intuitive properties only get us so far, and we're also interested in when the stronger condition holds, which is called this non-Archimedean inequality. And it's a strict strengthening of axiom 3, which states that the sum of the absolute value of this sum x plus y is always less than or equal to the maximum of the individual absolute values. And this is not so intuitive, because in the very simple example, let's take k to be equal to r and x equals y equals 1. Left-hand side would be 2, and the right-hand side would just be maximum of 1 on 1, which equals 1. And 2 is certainly not less than or equal to 1. Which means that the usual absolute value on the reals is not non-Archimedean. We say that it's just Archimedean. And you might have heard of the Archimedean property of the real numbers in like an analysis course or something. And this states effectively that you can scale any real number by some positive integer, say, to exceed any other quantity, any other real number. And this essentially pertains to the fact that this fourth stronger condition does not hold, where you're constraining it so heavily that the absolute value of a sum is less than or equal to both the individual absolute values. This is not something we're used to, so let's give an example of a non-Archimedean absolute value that can in fact be defined on any field. This is called the trivial absolute value, and we'll see why in a second. Let K be any field. We can define the absolute value to be trivial on a field by setting that for an element to be equal to 1 for any non-zero x, and to agree with the first axiom here, definiteness, 0 when x equals 0. So this is trivial, we're just blanket setting everything equal to 1 when we can, and 0 to be an absolute value in the first place. And let's look at a justification or a quick glimpse as to why this might be non-Archimedean in, say, the real numbers, which is something we're familiar with. So defining the trivial absolute value on R, we can take two elements that are non-zero and assume, just to avoid some technicalities for now, that they're not additive inverses. Here we see that since x plus y is non-zero, the absolute value here is going to resolve to 1. And because the individual elements are non-zero, their absolute values are both 1 each. This gives the implication that 1 is less than or equal to 1. And of course, equality holds here. This is strictly stronger. And there's a couple more cases that you can check. One or more of x and y can be 0, admitting additive inverses and so on. But in each case, you can show that this persists, and the trivial absolute value will be non-Archimedean always. Okay, so this is a good example to keep in mind. And next, we're going to look at a characterization of when absolute values on fields are non-Archimedean. And this lemma here states that an absolute value on a field is non-Archimedean if and only if the absolute value of the sum of 1 taken n times for any positive integer n is less than or equal to 1. So we take for any n, right, the sum end, when you take the absolute value, that being less than or equal to 1 is in fact necessary and sufficient to show that the absolute value in question is non-Archimedean. Okay, how do we prove this? The forward direction is more straightforward, let's say, than the converse, and this is a simple induction argument. So we assume k is non-Archimedean, and we want to show that this property in fact holds. One thing we need to show, and that's going to be quite important as well, is that the absolute value of 1 in the field is always equal to 1 in the reals. Here we can write the absolute value of any non-zero element x, I should have specified this here, is equal to absolute value of 1 times x. This is trivially x equals 1 times x. Then by homogeneity, splitting up this product into absolute value of 1 times that of x. And looking at this first and third elements of this equality chain here, we can just cancel out absolute value of x, which is why I said, by hypothesis non-zero x, just to avoid division by 0 or vacuous equalities holding. By canceling these out, we get 1 over here, and the reals is just equal to the absolute value of 1 here, and we've proven what we've wanted to. In fact, this provides us the base case for induction on n, where equality holds here when n equals 1. Now we can proceed by induction, where the induction hypothesis claims that this holds for some m greater than 1, and we want to show the same is true for m plus 1. So we take this absolute value of m plus 1 sum ends of 1. Using axiom 3, we split this up and write that it's less than or equal to the one consisting of m sum ends plus absolute value of 1. Because of what we've shown above, this term is equal to 1 itself, which we've written over here. And now by hypothesis, since k is, I should have written the absolute value on k is non-Archimedean. That's better notation. I've kind of abused it here. We know that this is less than or equal to the maximum of this absolute value consisting of m sum ends of 1 and 1. Now, we know by hypothesis, the induction hypothesis specifically, that this is less than or equal to 1. So at most, this is equal to 1, and the maximum is always going to just be 1 itself. This proves the forward direction by induction, because we've shown the base case and we've shown it holds for m implies it holds for m plus 1. Great. So how do we show the converse now? We want to show that if this property holds for any positive integer n, then the absolute value is non-Archimedean. This requires a bit of cleverness and a really cool argument here. Suppose that the property holds, and we, for now, fix n greater than or equal to 1 arbitrarily, so it doesn't matter here. For any pair of elements x, y, and k, now, we know the following chain of equalities and inequalities. We write the absolute value of x plus y to the nth power, where n is taken outside. By repeatedly applying homogeneity, we can in fact move this n on the inside and obtain that this is actually equal to the absolute value of x plus y to the n inside. By the usual binomial theorem, we can write this as equal to this following sum, and then by once again repeatedly or inductively applying the third hypothesis, the absolute value of the sum is less than or equal to the sum of the absolute values. We do this like n plus 1 times here, then we can bound it as follows. And the crucial part now is noticing this binomial coefficient is always going to evaluate to some positive integer number of sum ends of 1. And by hypothesis, each one is less than or equal to 1. So we can bound each of these sum ends by 1 times this, which is of course just this sum, and we can write that this holds. So we can notice that this is less than or equal to the sum from 0 to n, absolute value of x to the m of y to the n minus m. Once again, we apply the hypothesis by stating that this sum can be written like n plus 1 times, so there's n plus 1 sum ends in here, and this is going to be less than or equal to n plus 1 times the maximum of x, y to the n. This is by the non-Archimedean hypothesis. Oh, sorry, not hypothesis, this is just, we want to avoid that here. We want to show that it's non-Archimedean because of this fact that we can pull from this inequality. So now we focus on this first and last terms that we've gotten. By taking nth roots of both sides, we obtain absolute value of x plus y is less than or equal to this term times the maximum of these two, and we do the natural thing, which is to let n go to infinity. So as n grows large, we see that this limit goes to 1. One can work this out using a simple logarithmic argument, and we finally get the desired inequality. This shows that the absolute value is non-Archimedean on k. Once again, I wrote this kind of abusive notation here, but we've shown both sides of the lemma, and this proves that. Great, so what are some of the immediate consequences of this characterization? Well, two places that we can look immediately are finite fields and fields of positive characteristic. So, I immediately noticed that I've written this one wrong. So finite certainly wouldn't hold for all fields in general. We have two parts to this corollary. In a field of positive characteristic where you can take one added to itself p times, where p is, say, the characteristic of some k, that's going to be equal to 0, then we know that every absolute value turns out to be non-Archimedean here. Coming off of this, the only absolute value on a finite field is the trivial one. And just to clear things up, finite fields don't necessarily have to have positive characteristic. Consider like rational functions over some finite field, for example. So this is fine. So we have these two very important corollaries which characterize the simple nature of absolute values on certain kinds of fields. And now we introduce an equivalence relation on class of all absolute values. We say that two absolute values here and this primed one on a field K are equivalent if and only if there's some positive constant such that for every element, this resolves to be one is the power of another. So for any x in the field. So equivalence depends on one absolute value being the power of another on every element. This is clearly an equivalence relation, so you see reflexivity immediately because that's vacuous equality here. Just take alpha equals 1. You can see symmetry, just take the multiplicative inverse. So on one side, you just have alpha. You move this over to the other by considering 1 over alpha, the importance of having alpha positive. And transitivity is immediate. You just chain the two exponents, and you get that that's transitive as well. So this is, in fact, a well-defined equivalence relation. Okay, so now we take all this theory we've been looking at, all these definitions and terminologies, and apply it to characterize the absolute values on the rationals, which is the starting point to a lot of very important theorems and ideas. First, we denote the usual Archimedean absolute value on the rationals, which is inherited by the real, so just the one we're familiar with, as this absolute value sign sub infinity. The reason for this notation will become clear in a little bit. I hope to explain that then. But this is right now our notation for the Archimedean absolute value in Q. We see that there's going to be actually infinitely many others, and there's exactly going to be one for each prime. We quickly reiterate unique factorization. Any non-zero element of the rationals can be uniquely expressed as up to a unit, the product of prime powers, let's say. I've written Q because I'm reserving P for something in a moment, where Q is some prime, as Q varies, and E sub Q is the corresponding exponent that corresponds to the element that we've chosen in Q star. Now we define two very important ideas. One is called the p-adic valuation affixed to a prime P. So we define this to be a function from the rationals to the integers by v sub p of any element in Q star to be equal to the exponent that corresponds to the prime power that is exhibited in the element. And we also take nu p of 0 to be equal to infinity for a reason that becomes clear in a second. So this is the p-adic valuation, and it detects the highest power of some prime in a given element of Q star. It's extracting that, right? It's taking the order. Sometimes you will see this initially defined on just the integers, and you can extend this to the rationals by defining like some subtractive v sub p of a over b is v sub p of a minus v sub p of b. But right now we're just doing this directly from Q to Z. Now going off of the p-adic valuations, we're going to define p-adic absolute value. And this p-adic absolute value corresponding to, of course, any p prime is absolute value of x sub p, our notation that contrasts with this one infinite Archimedean prime, is going to be defined to be p to the negative valuation. So we also take the absolute value of 0 with respect to any prime which we see is coming out to be p to the negative infinity, we understand this to be 0. And now we see why we took v sub p of 0 to be equal to infinity for any prime, because this allows us to, in fact, define an absolute value where the absolute value of 0 is equal to 0, and it's going to be positive on every other element. So this defines an infinite class of other non-Archimedean absolute values on the rationals. So we have one for each prime, and we have that additional absolute value that's Archimedean induced by the reals. Great. So there are two theorems that come out of this. And first, before talking about both of them, I won't prove both rigorously. The first one is very involved, and I might attach that separately. And the second, I'm just going to give some examples, and hopefully it's clear why this helps. You can just show this by induction normally. Let's take x equals 18 over 25, which is equal to 2 times 3 squared divided by 5 squared, or I can write this 2 times 2 to the 1 times 3 to the 2 times 5 to the negative 2. So this is what we want to examine. And this is what we mean by taking that p-adic valuation. So at 2, since we take this prime power, we notice this is 1. That's what it comes out to. We see that the exponent of 3 in x is 2. And we see that the exponent of 5 is negative 2. So that's all this is here. And now we calculate the absolute values with respect to each of these primes. So with respect to 2, we have p to the negative v sub p of x, which comes out to 2 to the negative 1, so 1/2. For absolute value of x sub 3, the 3-adic valuation of x is 3 to the negative 2, which is 1/9. And the 5-adic valuation of x is 5 squared, or 25, because we have 5 to the negative 2, or 5 squared, 25. Great, so this gives some examples or some concrete things to look at, and it's straightforward to check that since there's no other primes in here, everything else will just be 1. Or, well, specifically, the valuations will all be 0, because you have p to the 0 equals 1, and these, since you're considering p to the 0 for all of them, the valuations are just going to be, the absolute values is going to be 1 for every other prime aside from 2, 3, and 5. This is the big classification theorem for absolute values on Q. This is called Ostrowski's theorem, and it states that every non-trivial absolute value on the rationals is equivalent to some p-adic valuation or the infinite inherited Archimedean absolute value. So this is the notation I'm using, p less than or equal to infinity, where we have either p prime or we admit the possibility of p equals infinity. So this is the classic, this is the big result that we want. And there's an associated result, which is the product formula. And we should pay attention to this one because it has a natural generalization to global fields overall. In fact, we're actually going to define global fields in a few lectures as those which have some kind of product formula which their elements satisfy. So this is very important, and after a few examples, hopefully it becomes transparent why this is a reasonable formula to expect. So for any x in, any non-zero rational number, we claim that the product over all valuations of x, I should be precise, over all p-adic absolute values, including the Archimedean one of x, this is going to equal 1, irrespective of x. So this is a big formula. And our first example, which we reiterate from here, we take x equals 18 over 25. This product, we want to only basically detect 2, 3, 5, and infinity. Respectively, we already calculated these here, so 1/2, 1/9, 25. This is 1 over 18. This is 25, so we get 25 over 18 times the usual absolute value, and this, of course, cancels out to give you 1. For a slightly more illustrative example, which I've written out in more detail, we can take x equals negative 72 over 245, which equals negative 2 to the third times 3 squared divided by 5 times 7 squared. And like above, I'll write this in this notation as well. Keeping track of these exponents. Then this product that we want to be equal to 1 is just that over x2, x3, 5, 7, infinity. And notice by what we said earlier, for any primes that are extraneous or not contained in the product or in the factorization of the number we're considering, the absolute value with respect to p there is going to give you 1, so it doesn't actually affect anything in the product. Here, the two-adic valuation is 1 over 2 cubed, 1 over 3 squared, 5, 7 squared, and these are each of the finite adic valuations. So we see that successively, these are extracting the presence of primes in its prime factorization bit by bit, and when we consider their product, it's putting them back together. Finally, the existence of this infinite Archimedean absolute value allows for this to multiply with the reciprocal as it's being decomposed here and cancel out so that it gives you 1. So we notice that this is just 1 over the number we considered here. Of course, the negative sign does not matter, which is why I included it here. And this will still give you 1 as everything cancels. Okay, so just to recap what we've looked at now in this past 20 minutes, we looked at what it means to have an absolute value on a field, and then we looked at the special case of non-Archimedean absolute values which satisfy a stronger sort of triangle inequality with their elements. We looked at a necessary and sufficient condition for an absolute value to be non-Archimedean on a field, namely if the absolute value of 1 added to itself any positive integer number of times is less than or equal to 1. Then we looked at, from this, two corollaries which have consequences for any positive characteristic field having certain kinds of absolute values. Namely, we see they have non-Archimedean ones only, and that the only absolute value on finite fields are trivial ones. We looked at equivalence of absolute values on a field, which is if one is always equal to some positive power of another. And finally, we embarked on the classification of absolute values on the rationals, where we designated the inherited one by absolute value sub infinity, used unique factorization to define the p-adic valuation and p-adic absolute value respectively, assigning to both some respective evaluation on 0 to make them make sense. And with the p-adic valuation and absolute value, we got two theorems, Ostrowski's theorem, which classifies everything as either some p-adic valuation for p finite or absolute value sub infinity. Or we have the product formula here, which says that the product over all absolute values for any element in Q star will be equal to 1. Okay, so we're going to take these ideas and keep them because they're going to be very important to us. And in our next video, we're going to look at discrete valuations on a field, which in many places should look reminiscent of what we've done today. And finally, we're going to use discrete valuations to define discrete valuation rings and detail many of the properties that make them so nice to work with. Discrete valuation rings are great, and we can actually realize them as localizations of a broader class of rings called Dedekind domains, in which there's a very nice analog of factorization. I don't want to give too much away on that front, so this is what we've got for this video, and I hope to see you in the next one. Thank you for watching.